to another video of this channel. So today we are going to take a brief detour into geometry land, and what we're going to do is we're going to solve this problem, and we're going to prove all of the theorems that we'll need to solve this. So we have to find the length of this angle bisector right here in terms of the sides A, B, and C of triangle ABC. So let's just recap. What is an angle bisector? Well, an angle bisector is a line from the vertex to the opposite side, also called a sevion, that divides this angle at the vertex in half. Okay, so let's just start going. And really, there's one big theorem that we always think of when we think of angle bisectors, and that is the angle bisector theorem. And the angle bisector theorem is what I'm going to prove to you right now. So what I'm going to do is I'm going to make a new copy of our diagram here, and I'm going to prove a relation between these sides, or maybe not these sides, but you'll see what I mean. And now I'm going to draw a line through C that is going to be parallel to AB. And then I'm going to draw the intersection point between this angle bisector and side BC and call this point E. Then I'm going to label side BE and sides EC as M and N respectively. And then we're going to draw an extension of line AE and call it intersection point with the line through C parallel to AB, F. So we have this complicated diagram that I explained in words. I mean, it's not that complicated really, but my explanation was a bit complicated. If you want, you can pause the video and quickly review this diagram before moving on. Okay, so what we're going to do is we're going to find a relationship between C, M, B, and N. And how are we going to do that? Well, when we think parallel lines, what do we think? We think, well, angles, right? Because we already have a bunch of angles. Maybe there's some alternate interior angles hiding here. And there are. Angles BAF and angles CFA are alternate interior angles, which means that they are congruent. And this is exactly why we drew this parallel line in the first place. Whenever you have angles in geometry problems, try finding parallel lines if they aren't already given to you. Okay, so we have this, but why did we draw that? Well, this is also a really common technique in angle bisector problems where we draw parallel lines is to find isosceles triangles. And here we have just found an isosceles triangle. AFC is isosceles because its two base angles are equal. What does that mean? That means that FC is equal to B. Okay, but now notice that angle BEA and angle CEF equal to the same things. I mean, they're congruent because they're vertical. And then we also have another pair of interior angles right here that I just highlighted. So what does this mean? That means that triangles BAE and triangles CFE are congruent, which means that the ratio of their corresponding sides are equal. So what do we get? We get B over N is equal to C over M. And that is called the angle bisector theorem. And we just drew this little proof square right here. So it's called the angle bisector theorem, and it's a really important tool in your geometry toolkit that you should really commit to memory. Okay, so we just took a quick detour and proved the angle bisector theorem, and now I'm going to prove a much less known theorem called Stewart's theorem. Now, Stewart's theorem has a proof that is really basic, but I mean not really basic. It does require some trigonometry, but it's quite straightforward. So why did I just erase these equal marks right here? Because Stewart's theorem works for any sevion D. Okay, and once again, we are going to draw M and N, but this time we're going to try to find a relation that relates C, M, A, N, B, and D. Basically all of the 5 lengths that I drew here. Okay, so how are we going to do that? Well, we are going to do a little bit of trigonometry here. And if you don't know your cosine rules, I think you should review them before moving on. So what we have is that this angle right here is theta, and this angle right here is 180 minus theta, because these two angles are supplements. Now we break out the law of cosines, and the law of cosines states that n squared plus d squared minus 2 times m times d times the cosine of theta is equal to c squared. And actually, just one quick fact. If you notice, the Pythagorean theorem is a special case of this theorem right here, because when theta is equal to 90, the cosine of theta is equal to 0, this whole term is equal to 0, and we get that m squared plus d squared is equal to c squared, which is exactly the Pythagorean theorem. Okay, so that was just one tiny proof of the Pythagorean theorem there. And now we're going to do the same thing on this triangle right here. Like that. So now what we're going to do, remember, we're trying to focus as less on angles as possible and as more on sides as possible. So you want to somehow get rid of the angles. And how are we going to do that? Well, we're going to start writing a new equation in orange, and we're going to pull everything that doesn't have to do with angles and only has to do with sides to this blue side of the equation here. So this yields cosine of theta is equal to c squared minus m squared minus d squared all over negative 2md. And we do the same thing for the cosine of 180 minus theta. Okay, so just like this, we have two equations. But is there really any relation between the cosine of theta and the cosine of 180 minus theta? Well, yes, that's why I told you to review your trig identities before moving on, because we have that the cosine of theta is equal to the negative of the cosine of 180 minus theta. So what does that mean? That means that these two equations are opposites, and we can completely get rid of the cosines. So I'm going to write this in a new color. I'm first going to write the right-hand side of the first equation, which is this. And this is equal to the negative of the right-hand side of the second equation. Now, why am I not writing the negative? You'll see. Because the negative that should have been in front of here, when there was a negative here, canceled with the negative that should have been here, so there are no negatives in here at all. And now we do some cancellation. It's all downhill from here. And we cross multiply, like this. And now we get rid of all the minus signs, because minus signs are worse than plus signs. And when we pull this term over, we factor like this. Now we rewrite this as nm. We're going to try to factor these two terms times m plus n. But notice here that m plus n is just equal to a. So this right here is equal to n times n, well, m times a. And then we do the same drill here. This is d squared times a, because m plus n is equal to a. And this relation right here, this is called Stewart's theorem. Now, this looks like a hard thing to remember, and I also thought that, but there's actually an acronym that you can use to remember it. CNC plus BMB is equal to dad plus man, right? This is just the reshuffling and removing the exponents of this equation. So that's how you can remember it, basically. And this doesn't only work for the angle bisector. This actually works for any Savian D. So we just proved Stewart's theorem, we also proved the angle bisector theorem, and those are going to be our two main tools that we will use to prove that, to find an equation for D in terms of A, B, and C. So to start off, we're once again going to label the sides M and N, like we did in all of these proofs right here. And now we're going to once again do some Stewart's theorem, D squared times A plus man is equal to c squared n plus b squared m. And now we're trying to find an expression for D. So what we're going to do is we're going to isolate the D. And we get this expression for D right here, which is quite hard to remember, and we wonder, is there a way we can simplify this? Now, in every single problem, when you are a bit stuck, you look for information in this problem that you haven't used yet. We haven't used the fact that D is an angle bisector. What does this mean for D? That means that this condition, the angle bisector theorem, is true. So once again, I'm going to rewrite the angle bisector theorem like this. And this yields that Cn is equal to Bm, right? By cross multiplying. So what does this yield? Well, the first term in this numerator right here, this turns into c times m times b. Why? Because c squared n is c times cn, but cn is mb, so this turns into c times m times b. We do the same thing for the second term. This is the same as bcn. Why? Because b squared m is b times bm. bm is cn, so this is the same thing as b times cn. And then we subtract m times a times n. We divide all of that by a. Now we factor. We have bc times m plus n minus ma n all over a. Now notice, this was also a technique that we used in our proof in the Stewart's theorem. I mean, it's not really a technique, it's just a fact that m plus n is equal to a, so we can actually turn this into bca and factor. Like this. The a's go away, and we have that d squared is equal to bc minus mn, yielding that d is equal to the square root of bc minus mn, and it's obviously equal to the positive square root since the length. Okay, so this is actually a really simple and really useful expression for d that still doesn't answer our question, because we want to find it in terms of a, b, and c. So when you know m and n, definitely use this expression, but if you know c, b, and a, there's actually is an expression that we can use to find d just in terms of those lengths. Now notice, this fact can be easily proven using the angle bisector theorem. I'm going to leave its proof to you guys. So what we have is m over c is equal to a over b plus c. So what does this mean? That means that this part to this part is the same as this whole to this whole right here. And the same actually goes for n. And once again, this can be easily proven using the angle bisector theorem, so I'm not going to prove it here. But this fact is true, just to let you know. So what we do now is we isolate the m like this, we isolate the n like this, and now we substitute. So we have from all of this that d is equal to the square root of bc minus c times a times a times b, which is bc times a squared, all over b plus c squared, right, because it's multiplied by itself. This may seem a bit hard to remember, but we're going to factor out a bc inside the radical, and we get that bc times 1 minus a squared all over b plus c squared, and the square root of that is equal to d. So this is also an identity that we have, and this can also be remembered when we have just these sides. I mean, if you have trouble remembering this, you can always just remember this and use this fact to quickly derive this. It only takes like a couple seconds, so it's a really quick thing. Anyway, so just now what we did is we took a very big tour through geometry land, proved all these theorems, and found a really nice expression for the angle bisector of a triangle. So I really hope you liked this video, and I'm going to see you in the next one. Wait a second. Don't leave yet. I have a challenge for you. Can you find an expression using Stewart's theorem of the median of a side? Leave your answer in the comments, and I'll check them and tell you if you're right. Okay, bye for real this time, and thanks for watching. See you in the next one.